Hi, this is the video for assignment 58, where we're talking about partial fraction decomposition. And it's okay if at this point you say, huh? Because even though you know these words, you may not know what all of them taken together mean in math land. I don't think you've ever seen this before. So let's take a look at it. It turns out that there's something we do in calculus uh, really commonly that suddenly we're not going to be able to do in calculus unless we first do partial fraction decomposition. All right. So I'll get into that first, but I was wondering if you could take this expression, little bell work, this expression, 1 over x minus 1 minus 4 over x plus 6. Could you simplify this expression? I know we did this earlier in the year in the Algebra Basics section. Um, just a little review. Please simplify the expression by combining this into one fraction. Okay? Give it a try. Come back when you're done. Oh, it's true. There's no equal sign here. And because there's no equal sign, this isn't solving. This is simplifying. If there were an equal sign and something on the other side, I could multiply every term by the least common denominator. But since this is simplifying, I have to make a common denominator. I have to multiply by a version of 1 over here and a version of 1 over here. Okay, so what are we going to get there? We're going to get x plus 6 minus 4, x minus 1 over our common denominator, x plus 6 and x minus 1. Please don't cancel those. No. In fact, angry ears. You get angry ears when you do that. That's really bad. And really, you need to stop that, actually. Um, if you can't factor cancel from all the terms, stop it. No, not okay. Um, Instead, sometimes what happens is it brings people back to where they started. But that's only when it works out well. Sometimes when you do that, you just end up in this place that's just not good. Don't do it. Please don't forget to distribute the negative 4 to each of these. So we're going to end up with x plus 6 minus 4x plus 4 over x plus 6, x minus 1. Okay? And we still have some like terms we can combine here. We get negative 3x plus 10 over x plus 6, x minus 1. Oh, nice. And I could, of course, FOIL that out. Negative 3x plus 10 over x squared plus 5x minus 6. I like it. Okay, so this method where we simplified by combining by making a common denominator and then uh, putting these two different fractions into one fraction. Good. Now, instead of going this direction, like we did in the Algebra Basics unit, now what we need to do is start here and get us to here. We want to decompose this one fraction into these two partial fractions. We want to start here and we want to end here. Okay, well, let's see what I mean by when I say that. Um, you know, I think the way that I think about this task um, is that I have a loaf of bread. Tasty bread. I have a loaf of tasty bread. And it's so tasty, I think to look at the ingredients. And conveniently, I can look up the ingredients. And I see that this tasty bread, which I can eat and does taste great, it contains enriched wheat flour, and it contains rye flour. Flour. Sorry, not talking about botanicals here. Flour. And I can taste both of these flours in this tasty bread. But what I don't know is how much of each of these flours make up this bread. And so what I'd really like to do is be able to make this bread at home. And so I need to sort of reverse engineer the recipe just from tasting the tasty bread. Well, we're kind of doing that with this partial fraction decomposition. We're starting off with negative 3x plus 10. And we want to break it down into some amount of, these are my flours, some amount of wheat flour and some amount of rye flour. Partial fraction decomposition. I'm decomposing this one fraction into these two made up with these nifty little partial fractions. Okay? So, this, by the way, is called case 1. Case 1 is all about linear factors. See how I have these linear factors? They're all y equals mx plus b kind of things. Well, when I have these linear factors, I take each linear factor and throw a letter on top of it. That's it. If I had a third linear factor here, you know, an x minus 2, sure, I put a plus c over x minus 2. No, it doesn't matter which letter goes over which of these factors as long as each of these factors has its own letter. It may turn out that these letters are the same number when we're done solving. It may turn out that they're all 3 different numbers. Okay? But our goal now that we have this setup, a letter over each of these factors, so we can split into, so we can decompose into these partial fractions. Now I see this. Remember what we do when we have an equal sign? When we have an equal sign and rational functions, we can multiply everywhere by that least common denominator. And so what's going to happen? The x plus 1 is still there. So a times x plus 1. And here, that's, sorry, that was a minus 1. And here we have b x plus 6. Over here, all of this stuff cancels with all of this stuff, leaving me just minus 3x plus 10. All right, so we've got minus 3x plus 10 equals, well, yeah, plus b x plus 6. Now comes a fork in the road. There are 2 methods that I would encourage you to consider using when working on these partial fraction decomposition problems. The first method, I like to call magic numbers. And mathematicians hate it when I call magic numbers because there are no magic things in math, except, you know, there are, and I believe it, so that's why I'm saying magic numbers. But magic numbers are numbers that make things disappear. And here in this line, I think x equals 1 is a magic number. How come? Well, if I plug a 1 in over here, I get 1 times negative 3 is negative 3 plus 10 is 7. Nothing disappeared there. I got you. But if I take this 1 and plug it in here, 1 minus 1 is 0. And 0 times a is 0. So that disappears. And I plugged in a 1 here. 1 plus 6 is 7. 7 times b is 7b. Divide both sides by 7, and I get b equals 1. By using a magic number, I was able to solve for b. No, don't count on these being the same. No, really, don't. But is there another magic number we could use? Something to make b disappear. What could make b disappear? I agree. If I used an x value of -6, -3 times -6 is positive 18. 18 plus 10 is 28. And over here, if I plug in a -6, -6 minus 1 is -7. Don't forget times a. And here, if I plug in a -6, -6 plus 6 is 0. 0 times b is 0. We made the b disappear by plugging in this magic number. When I divide both sides by -7, I get that a is -4. Now I'm almost done. I need to take these values and plug them back in here. So my answer is going to be, my partial fraction decomposition is going to be -4 over x plus 6 plus 1 over x minus 1. This is my partial fraction decomposition. And you may remember, this was the problem we started our Bell work with. We started with these two fractions and we combined them by making a common denominator to get this thing up here in red. In our problem now, using partial fraction decomposition, we're starting with this red thing and we're decomposing it so we can get the fractions that make it up. Okay? And when we get to this place in calculus, yeah, it's going to be the case where I can't do my calculus thing on this, but I can easily do my calculus thing on this. Easily do my calculus thing on this. On this, oh my goodness, no. Please don't do that. Piece of cake here. So we will need this skill. So this was case 1, non-repeated linear factors. I have an x plus 6, I have an x minus 1. These are different things. I just throw a letter on top of each. Okay. Well, how about you try this one? No, it'll be good, really. Good try. Okay, so I've got x over x squared minus 5x plus 6. What do we do first? Yes, you have to factor that. This is going to be x over x minus 2, x minus 3. Okay, now what? Well, remember, these are my linear factors. I need to put a letter over each of them. You can, change those letters if you want. Doesn't matter to me. Same answer when we're all done. Okay? So, what was next? Well, we want to solve for these letters. And the way we do that is, because of this equal sign, we want to multiply everywhere by our least common denominator. Okay, so my least common denominator, x minus 2, x minus 3, x minus 2, x minus 3, and here as well, x minus 2, x minus 3. Ooh, right there at the end. So what cancels? Well, all that cancels, leaving me just this x. And over here, this and that, is b times x minus 3. And then this plus sign, and then that a, and then this cancels that, leaving me just x minus 2. Okay? So what are my magic numbers? Well, I could use 3 as a magic number. Because if I plug a 3 in here, 3 minus 3 will be 0, and then b will disappear. So x equals 3. Now, that means I'm going to plug in a 3 for every x value, including that one. 3 equals 3 minus 3 is 0. 0 times b is 0. That's all gone. So next I'm over here with a. 3 minus 2 is 1. Oh, look, my a value is 3. Do we see another magic number? What will make a disappear? Right, x equals 2. will make a disappear. Because 2 minus 2 is 0, and 0 times a, poof, no more a. So I'm going to plug a 2 in for these x's. Now here, 2 minus 3, that's going to be negative 1 times b. So negative b equals 2. And if we divide both sides by negative 1, we get b equals negative 2. Great. We know our a value. We know our b value. We can be almost done as soon as we take these and plug them back into the black expression here. Our b value is negative 2. So we had negative 2 over x minus 2. And our a value was 3 over x minus 3. Yeah, look, same sign, same number. Not same sign, same number. Please don't read anything into this. You'll just be sad if you do. There's my partial fraction decomposition. Now, I did say that there was another method. Magic numbers is my preferred method for case 1, the case where I have non-repeated linear factors. Okay? But what if instead I wanted a different way? Maybe I'm not comfortable with these magic numbers. Okay, so I've got x, x minus 2, x minus 3, and over here we said b x minus 3 plus a over x minus 2, and we multiplied everywhere by our least common denominator, x minus 2, x minus 3, x minus 2, x minus 3, and again x minus 2, and x minus 3. And suddenly all my denominators disappear, and I'm left with x equals b, x minus 2, plus a, x minus 3. So everything's the same up to this point. It's only now that I have to choose. Am I going to use magic numbers, or am I going to use systems? Systems. I know, you really like magic numbers. Why would I want to do anything else? It turns out that by the time I get to case 4, I never want to use magic numbers, ever. I only want to use systems. And cases 2 and 3, it's hard to tell. I switch back and forth. So how does systems work? Well, systems starts by distributing. Okay, so I distribute. I get x equals bx minus 2b plus ax minus 3a. And now what I want to do is I want to group this into some different equations. The first equation is just going to have x stuff in it, like this, and this, and this. I'm going to say that the x stuff on the left needs to equal the x stuff on the right. And I'm going to say x equals bx plus ax. Okay? You could even divide everywhere by x and end up with x divided by x, b plus a. And that's one equation in my system. I also need to take all this not x stuff. Do you see any over here? No, me neither. It's 0. So 0 equals minus 2b minus 3a. And this is my second equation. I'm going to take these two equations that have two unknowns, and I'm going to solve that system. So we haven't reviewed solving systems yet. We will right at the end of the semester. But I like to think that you remember elimination or substitution enough to pull this off. So if I were doing substitution, I would probably subtract b from both sides, and I would know a equals 1 minus b. And so then I can replace this a with 1 minus b. I'll distribute that negative 3, and I'll have 0 equals minus 2b minus 3 minus a minus plus 3b. I'll combine like terms. 0 equals b minus 3, and so b equals 3. Great, so there's my b value. b equals 3. Now, if I take this b value and plug it in over here, 3 plus what equals 1? Well, it should be negative 2. 3 plus a equals 1. Yep, 1 minus 3 is negative 2. And so we get a equals negative 2. This method is called systems. I used substitution right now, but you could certainly solve this with elimination. And by this, I mean the little system you've got here. So we've got 1 equals a plus b, and we've got 0 equals minus 3a, minus 3a, minus 2b. Now, remember from systems, we need these coefficients to be either the same or opposites, or we need these coefficients to be the same or opposite. So I'm going to multiply everything up here by negative 2. Here, here, and here. So my first equation now will be negative 2 equals minus 2a minus 2b. And this one is still 0, minus 3a minus 2b. And I'm going to subtract this minus this, negative 2. This, negative 2a, minus a minus 3a, is going to be 1a. And here, minus 2b minus a minus 2b, they cancel, and I've got that. So elimination is pretty good here. And remember, with elimination, once I found one of these letters, I'm going to plug that a value back into either equation to find my value for b. Okay, and we already know that b equals 3. So if I plug my negative 2 in here, negative 2 equals negative 2 times negative 2 is 4 minus 2b. I subtract 4 from both sides. I divide by negative 2. And look, negative 3 divided by negative 2, that's going to be equal to 3. And so 3 equals b. Okay? So it may be useful to have, to use systems. Now, again, with case 1, yeah, I don't do systems. I always use magic numbers because magic numbers is really fast for me. But I can use systems if I need to. All right, so let's take a look now at case 2. Case 2 is repeated linear factors. And what do I mean by that? Well, let's take a look at this one. 5x plus 3 over x minus 1 squared. Or 5x plus 3 over x minus 1 times x minus 1. They're linear, but they're the same. So this is repeated. The setup is similar, but also a little different. I'm going to take a over x minus 1. I'm not going to put b over the other. That's not what we're going to do. What we are going to do is put a b over x minus 1 squared. Okay? Let's imagine this problem. 5x plus 3 over x minus 1 to the third. In this situation, I would have a over x minus 1, b over x minus 1 squared, c over x minus 1 to the third. Whatever that power is, that's how many fractions I need. And I need to represent all the different power possibilities. First degree, second degree, third degree. Because really, I don't know. I'm trying to make this loaf of bread. I know it's made up of a bunch of types of flour, like enriched white, bleached white, and white flour. Well, maybe, I don't know, all I saw was white flour. So I have to consider all of these. It may turn out that b is 0. It may turn out that c is 0. It may turn out that a is 0. At the beginning of the problem, I don't know. And so I have to lay out all the possible combinations. Okay? That's what case 2 is about, when I have repeated linear factors. Now, if we go back up here to our original problem, really, the method is still the same. Oh, look, I've got this equal sign, I have these fractiony things, and so what I'm going to do is multiply by the least common denominator. It's not just common denominator, it's least common denominator. And I'm making these noises because my least common denominator is not this times this. If you multiply everywhere by this times this, you are going to be tears of small child. No, bad, don't do it. That's not the least common denominator. Right here, that's our least common denominator. I'm going to multiply everywhere by x minus 1 times x minus 1. And when I do, these go away. 5x plus 3. This cancels one of those, ax minus 1, plus these cancel all of these, b. And again, we can think about using magic numbers here. We can think about using systems here. If I use magic numbers, I see x equals 1 would be a magic number, but I don't see anything that'll get rid of this. See, sometimes magic numbers doesn't fix it all. So let's try this with both magic numbers and with systems and see how it goes. With magic numbers, I'm going to say x equals 1 because 1 minus 1 is 0 and 0 times a, gone away. All I have is that b left over. If I plug a 1 in over here, 5 times 1 is 5 plus 3 is 8. And over here we have 0 plus b. And that's pretty fast. But now tell me, how are you going to solve for a? So here's what I need. I need a not so magic number. And my not so magic number, any number you want except that magic number you've already used. I like 2. I know, you would have thought I liked 0, but I like 2 because 2 minus 1 is positive 1a. And I would much rather work with a positive number than with a negative number. If I plug in 0 here, I'm going to have negative a. So I'm going to say x equals 2. And you can set whatever value you want as long as it's not x equals 1. So if I plug in x equals 2, I get 13 equals 2 minus 1 is 1 times a. And don't forget plus b. I know, we can't solve this yet. However, look over here. We know that b is 8. So I can do a little replacement, substitution, and I get that a equals 5. And so then my answer is going to be, or my partial fraction decomposition is going to be, a was 5, and our b value was positive 8. See, these have no, I don't see any connection. Again, you can check to see if this really is the partial fraction decomposition by making a common denominator. No, not this times this. This is the common denominator. You just need to multiply here by x minus 1 over x minus 1. That should bring you back to the original problem. If it doesn't, there's a mistake somewhere. Okay, so here was magic numbers. What about systems? Well, let's take a look. Systems, I wanted to distribute 5x plus 3 equals ax minus a plus b. I'm going to make an equation out of this x stuff. 5x equals ax. I divide both sides by x. I see that a equals 5. Now let's make an equation with the stuff that doesn't have any x's. 3 equals minus a plus b. We know a is 5, so let's plug 5 in there. And I need to solve for b. Well, if I add 5 to both sides, I get 8 equals b. That wasn't so horrible, was it? And I didn't have to use a not-so-magic number. So the choice is yours in case 2, whether you're going to do magic numbers or whether you're going to work on systems. Okay? All right. So let's see what you can do with this case 2 problem. I've got negative x plus 1 over x plus 2 squared. All right. Hey, do me a favor. For this one, I do want you to do this problem, but stop doing what you're doing and play the video again so that we can check to make sure we have the same setup. Really, I don't want you wasting time. These problems take a little while. I don't want you wasting time with the wrong setup. Okay? So pause the video, do the setup, put the video on again. That's the setup I have. Okay? I have to represent each possible power. Sorry about that, Ray. Each possible power combination. So I have first degree, I have second degree. If this was to the third, I'd need a plus c over x plus 2 to the third as well. All right. Okay, pause the video again, go back and solve. All right, so I need to multiply everywhere by my least common denominator. I know that some of you are ignoring me right now, and therefore you will get stuck later and be sad, but it's only because you are ignoring me now. One of these cancels one of those. And here, these cancel these, and I just have b. Okay, what are you going to use? Well, I've only got one magic number in this situation. So, I'm going to use systems. Actually, I wasn't sure. I thought I was going to say magic numbers. Maybe I still will. Yeah, minus and minus. I don't want to put a negative 2 in there. So I'm going to do systems. So I'm going to have negative x plus 1 equals ax plus 2a plus b. And now what? I want to group the stuff that has x's together. Negative x equals ax. Divide by x, divide by x, and I get a equals negative 1. Now I want to take all the stuff that doesn't have an x attached to it and put them together. There's my a value, so let's plug that a value in there. And so I've got 1 equals negative 2 plus b, or b equals 3. And I'm almost done. Remember, I just need to replace this a and b with these values. So negative 1 over x plus 2 plus 3 over x plus 2 squared. I can't do my calculus with this thing. I can easily do my calculus with this thing. Okay? Okay. Woof. I kind of feel like we should do one more. Maybe two. All right. I think what I'm going to do instead is I'm just going to introduce the other cases. So let's take a look now at case 3. Oh, by the way, you know, we could actually have a situation like this. X squared minus x minus 8 over x plus 2 squared. So this is kind of a combination of case 1 and case 2. See, that's not repeated. See, that one is repeated. The setup, though, you know, is like that. I still want to multiply everywhere by my least common denominator. My least common denominator is not this times this times this. That gets you in trouble. Right here. This is my least common denominator. So I'm going to multiply everywhere by x times x plus 2 squared, x times x plus 2 squared, x times x plus 2 squared, and x times x plus 2 squared. These cancel these. We've got x squared minus x minus 8. And this cancels that. A x plus 2 squared. This cancels one of those. B x plus 2. And these cancel all of these, leaving us just with cx. Okay, now let's talk magic numbers. Magic number negative 2. Negative 2 will get rid of all that stuff and leave me just this. X equals 0 will get rid of all that stuff and leave me just this. So I got two magic numbers, but three constants to find. All right. If I were doing systems, and I could do systems here, if I were doing systems, I'd have to FOIL this and then distribute the A. I have to distribute the BX to each of those and then combine like terms. I don't really want to do the foiling, so I think I'm going to take the magic number approach in this situation. X equals negative 2. Negative 2 times negative 2 is 4. Negative 2 times negative is plus 2, so 4 plus 2 is 6. 6 minus 8 is negative 2. Okay, negative 2 on that side. And over here, if I plug in a negative 2 plus 2 is 0, so all that goes away. Negative 2 plus 2 is 0, so all that goes away. So just a negative 2 times c. And if I divide both sides by negative 2, I see that c is equal to 1. And what was the other magic number? The other magic number I talked about was, what will make this disappear? What will make this disappear? X equals 0. If I plug a 0 in for all these x's on the left, I'm going to have negative 8. If I plug a 0 in here, this goes away. If I plug a 0 in here, all this goes away. If I plug a 0 in here, 0 plus 2 is 2. 2 squared is 4. 4 times a. And when I divide both sides by 4, I get negative 2 equals a. Fabulous. But what about my third constant? I need to find b, and I've used up all my magic numbers. Well, here is where you use a not-so-magic number. Pick any number you want. Negative 1 might be good, because negative 1 plus 2 is 1. We've already used 0. Most people, I think, use 1. We're looking for any number, and these are generally the two numbers that are most often used here. This one certainly because it was a magic number, and this one because it's a number that's easy to work with. People feel comfortable with it, as opposed to negative 1, which would be smart to use, but generally people don't think to use negatives. So if I plug that 1 in for all these x's, I'm going to have 1 minus 1, 0, minus 8. Negative 8 there equals a. 1 plus 2 is 3. 3 squared is 9. 9a. And then here, 1 plus 2 is 3 times 1, so I get 3b. And 1 times c. Okay, well, luckily we know what c is, and we know what a is. So I'm going to plug a value in there, and here I'm going to plug in this value. So negative 2 times 9 is negative 18. I could combine like terms. Negative 8 equals negative 17 plus 3b, and then I'll add 17 to both sides. And what do I get? I get 9 equals 3b, or b equals 3. And that's great. I've got all three of my constants. I can go back to my original problem, plug a negative 2 in there, a 3 in there, and a 1 in there. So I'm going to have negative 2 over x plus 3 over x plus 2 plus 1 over x plus 2 squared. Partial fraction decomposition, there you go. So this was a combination of our repeated linear factor, case 2, and having some non-repeated thing. Okay? All right, so case 3. Case 3. And I will tell you that case 3 and case 4, you don't have to stress about them on our CFA. I think for our purposes, just seeing that they exist and how they work and how they're consistent, that'll be enough. Okay? All right, so case 3. Case 3 is non-repeated, irreducible quadratic. What do I mean by that? Well, what I mean is when I have something that's a quadratic that I can't factor. So, for example, and factor with real numbers is what I'm talking about. So, for example, if I have something like 3x minus 5 over x to the third minus 1. Now, that's a difference of cubes. I know how this factors. It factors as x minus 1 times this 1 squared, change the sign, and this 1 squared. And that, no problem, a over x minus 1. But this, yeah, that's a problem. Because remember when we were doing the factoring, I said this only factors with imaginary numbers. So we're calling this an irreducible quadratic because we can't factor this with real numbers. So what do we put on top? Plus 1. It's not b. Sorry. Yeah, it's not b. So here's what I want to say. Remember when we had this problem and we said minus 3x plus 10 over x plus 6 and x minus 1. And I said, hey, what about a over x plus 6 and b over x minus 1? Right? Okay. What degree x do you see here? I know, it's a really hard question for a lot of people because they don't see an x there. That's right, because it's x to the 0, and that's x to the 1. See how this degree is 1 less than this degree? Well, this degree has to be 1 less than this degree. So, do I write bx? Well, close, but no, that's not right either. This bx, that if we graphed it, would be a linear equation with a slope of b that passes through the origin. And remember me saying we don't know what this is going to break down to, so we have to consider all the possibilities. Have you ever graphed a linear equation that didn't pass through the origin? Because bx always passes through the origin. It may have a different slope, always going to pass through the origin. Have you ever graphed a linear equation that didn't pass through the origin? Of course you did. And for that reason, we have that. Sure, 1 degree less than that x squared, but I have to consider all the possibilities. Okay? Yeah. Now, the mechanics of this, yeah, no problem. I'm going to take my least common denominator and I'm going to multiply everywhere by it. So I've got x minus 1 and x squared plus x plus 1. And when I multiply here by that, all of those cancel. I have 3x minus 5. Here, where I multiply by this times this, the x minus 1s will cancel, leaving me a x squared plus x plus 1 plus sign. And then here, when I multiply by this times this, these will cancel, leaving me that x minus 1 times this stuff. Be careful. I'm going to say that again. Be careful. All of this stuff is being multiplied times x minus 1. All right, so there's our setup, and now it's time to choose, do you want to use magic numbers, or do you want to use systems? So here's what I see. X equals 1, x equals 0, because 0 will make b disappear. I've got 2 magic numbers. I've got 3 constants to solve for. Which would you like to do? Should we do both and compare? We can do that. Okay, so magic numbers first. X equals 0. Do I like x equals 0 first? No, I like x equals 1. Good. So 1 times 3 is 3. 3 minus 5 is negative 2. And then we've got this a. I'm plugging in a 1 for all of these x's. So 1 plus 1 plus 1 is 3a. And then here I'm plugging in a 1 for x. So I'm going to have b plus c. But 1 minus 1 is 0. So 0 times b plus c, all that goes away. I just have this. I divide both sides by 3, and that's my a value. Nice. Love magic numbers for that. X equals 0. Okay, that disappears, that disappears, that disappears, that disappears, that disappears. And so what I'm left with is negative 5 equals a plus, this disappeared, and I've got minus c. Conveniently, I know what a is. So I'm going to plug my negative 2/3 in here. And yeah, look, minus, minus, minus. Just divide everywhere by negative 1. Now I'm going to subtract 2/3. How many thirds is 5? It's 15 thirds. 15 thirds minus 2/3 is 13 thirds, so C equals 13 thirds. I've used up my 2 magic numbers. What do I do now? Well, now I need that not so magic number. And really, it doesn't matter what you choose, though. I like 2, because 2 minus 1 is 1. And it's easy to multiply things by 1. So I'm going to go with x equals 2. 6 minus 5, 1. 4 plus 2 is 6, plus 1 is 7a. 2 minus 1 is 1 times each of these things. Don't forget to put the 2 in there. So we have 2b plus c. Well, luckily, we know what a is, and we know what c is. So 7 times negative 2/3 is negative 14 thirds, plus 2b plus 13 thirds. That's 13 thirds. And on the other side, we have 3/3. Okay, if I combine like terms here, I'm going to have negative 1/3. I add 1/3 to both sides, 3/3 plus 1/3. I've got 4/3 equals 2b. And if I divide by 2, I get that b equals 2/3. Now, if you're looking this up in the back of our textbook, you're going to see something different from what most students write. Most students say, okay, I've got this value of negative 2/3 for a, so I write negative 2/3 over x minus 1. And then our b value turned out to be 2/3 x. Our c value was 13 thirds. I feel like something was negative and I've lost it. That was negative because the a value was negative. Okay, great. And all of that is over x squared plus x plus 1. That's the way most students write it. The textbook, they don't like these fractions. So they write this. Notice how each of these are thirds. So they're going to have the 2x and the 13 on top, but they're going to put the 3 on the bottom. Okay. Either way is fine by me. But you should be aware that, if you see this, it's likely to be written like this. Okay. So we had gone through and done this with magic numbers. We used 1, we used 0, and then the not so magic number of 2. I also said I would take a look at this one with systems. So with systems, I've got to FOIL and distribute. But I think I want some more space. So I'm going to have 3x minus 5 equal ax squared, bx plus a plus bx squared plus cx minus bx minus c. All right, systems. Ew. So let's group all the stuff that doesn't have an x together. So that's going to be negative 5 equals a minus c. And now let's group all the stuff that has an x to the first together. X to the first, x to the first, x to the first, and x to the first. So my next equation is 3x equals, oh look, plus bx minus bx. Can that be bx? No, that's ax. Sorry, That was bad distributing, foiling on my part. Because remember, that came from this times each of these. There's the ax squared, there's the a, but what about here? It's a times x, and so that needs to be ax. So I get ax plus cx minus bx. And I could divide everywhere by x and be left with 3 equals a plus c minus b. Fabulous. There's my x to the first equation. This is my I don't have any x's equation. What about these x squareds? Well, I want to set these x squareds equal to, that's right, there are none over there. And because there are none over there, I'm going to say 0 equals ax squared plus bx squared. And if I divide everywhere by x squared, I get 0 equals a plus b. And I need to solve this system of 3 equations and 3 unknowns. My suggestion is that you use substitution here. Find out that b equals negative a. Find out that c equals a plus 5. And plug those things in. So the equation would now be 3 equals a plus, c is equal to a plus 5. And our b value is negative a. But we want negative b, so that's going to be a positive a. So what do we have? Well, I see here that I've got 3a plus 5 equals 3. If I subtract 5 from both sides, I get negative 2 equals 3a, or a equals negative 2/3. Hey, that's what we got with magic numbers. And now I still need to find b and c. If I take this a value and plug it in here, because this says c equals, I'm going to have negative 2/3 plus 5, which is going to be c equals 13/3. And here, I know that b equals negative a. This is a. Negative a flips the sign, and I end up with b equals positive 2/3. I can do this problem either with system or magic numbers. And this one kind of felt faster and easier with magic numbers, but it's not always that way. So, yeah, gotta kind of juggle. Okay, so will you do the setup? Will you do the setup? Don't solve for a, b, and c. Will you do the setup for 3x squared plus 4x plus 10 over x plus 1, x squared plus 1. Okay, pause the video, do the setup, come back when you're done. Hi, welcome back. That's case 1. That's not quadratic. That's case 1. This is case 3. Non-repeated irreducible quadratic. I can factor that as a difference of squares only if I use magic numbers. I mean, if I use imaginary numbers. And I'm not doing that. So my setup is a over x plus 1 plus bx plus c over x squared plus 1. Remember, I need something that's 1 degree less than this thing on top. And not all lines go through the origin. Some are shifted up, some are shifted down. So I need to have the widest possible options in setting this thing up. Because I don't know. Maybe this. Maybe this. Don't know. Won't know until I go through the process. So I have to start setting this up. The setup has to include the potentiality for both of those things. Okay? All right. I will quickly go through this one. And then we'll say a little word about case 4. So my least common denominator, this times this. I see it right here. This, whatever's over here, is always the least common denominator. So if I multiply by x plus 1 times x squared plus 1, x plus 1, x squared plus 1, and here, x plus 1 times x squared plus 1. The x squared plus 1's cancel, and I'm left with bx plus c times x plus 1. Plus, here, the x plus 1's cancel, and I have a x squared plus 1. And here, all this cancels with all that, leaving me 3x squared plus 4x plus 10. Okay, what do you want to use? Magic numbers? Systems? My guess after the last problem is that most of you want to use magic numbers. So what are the magic numbers? -1 will turn this into a 0. 0 times these things, they all go away. And x equals 0 will make b go away. So I'm going to use 0 and -1. Okay, so if I start with x equals -1, I have to plug that -1 in everywhere. 3 minus 4 is -1, plus 10 is 9. -1 times -1 is 1. 1 plus 1 is 2. Plus, I'm plugging in a -1. -1 plus 1 is 0. And 0 times this stuff all goes away. So a equals 9/2. We also said magic number x equals 0. 0, 0, I got 10. 0 plus 1 is 1. 1 times a. 0 makes that disappear. 0 makes that disappear. And we just have c times 1. And don't forget that plus sign. All right, well, we know what a is. 10 equals 9/2 plus c. I really like the approach where we multiply everything by that least common denominator. And so I end up with 20 equals, sorry, those cancel, 9 plus 2c. Subtract 9 from both sides, and I get that c equals 11/2. Well, great. Now I know what a is and what c is. So how do I find b? Well, I have to use a not-so-magic number. What would be a good not-so-magic number to use? Well, yeah, no, I've already used -1. I've already used 0. I guess I'm going to go with x equals 1, because then this just becomes 17. 1 plus 1 is 2a, plus 1 times b is b, nice, and then 1 plus 1 is 2 distributed to each of those. So 2b and 2c. So now when I plug in my c value and my a value, I've got 17 equals 2 times 9/2 plus 2b plus 2 times 11/2. Oh, how convenient. I get 17 equals 9 plus 2b plus 11. 9 plus 11 sounds like 20 to me. 17 equals 20 plus 2b. If I subtract 20 from both sides, I get -3 equals 2b. And so we know that b equals -3/2. So there's my a, there's my c, there's my b. I'm not done until I take these and plug them back in here. So what should this look like? Well, when we're all done doing our partial fraction decomposition, we should have 9/2 over x plus 1 plus -3/2 x plus 11/2 over x squared plus 1. Again, the textbook isn't going to leave like this. I think this is fine for our CFAs. 9 over 2 x plus 1 plus -3x plus 11 over 2 times x squared plus 1. All right. Well, that's case 3. And I don't plan on giving you any of those this year. No, definitely not this year. Case 4. Case 4 is repeated irreducible quadratic factors. So if I have something like this, x to the third plus x squared over x squared plus 4 squared. Well, look, that's a sum of squares. This only factors with imaginaries. And I've got it squared. So we have to represent all the power possibilities. ax plus b over x squared plus 4. But I could also have that x squared plus 4 squared case. And up top, cx plus d. And if you want to know why that's an x to the first, even though it looks like I'm going to have an x to the fourth down here, and that wouldn't be 1 degree less, you let me know and I'll clarify that for you. But I'm sticking with whatever this power is, I need to have that many fractions, and this says 2, so this has to be 1 degree less. And then all of these will be linear. Okay? All right. Well, I don't expect you to see any case 4s in our class, and generally speaking, when you have a case 4 in calculus, you can usually get around having to do partial fraction decomposition. But case 1, whew, terribly important. Case 3 is kind of important too in calculus. All right, well, I hope this was informative. Like, in my mind, this is kind of like the new thing. Everything else we've talked about so far, I'd like to think you've actually done before, including, yes, all that transformation graphing. Yeah, you've supposedly been doing that since Algebra 1. And if you haven't, that's not cool. Okay, let me know if there's anything I can do. See you later.